Radical Dude here, and today we're going to prove volume of a sphere. Now most of you know what the volume of a sphere is. You know it's 4/3 pi r cubed. But what I'm going to try to do is show you why that is. Where did that come from? So first let's draw a sphere. Okay, so what we got to do is try to draw a sphere. It's very difficult to do because we're drawing 3 dimensions on a 2-dimensional surface. So let me make this big. Let's do this. Here's your little sphere. Right? And what we're going to do is we're going to take a cross-sectional area of the sphere. Let's make this, your radius. So if I take a little circle, we're doing cross-sectional areas. So let me do a little circle like that. And it has a little bit of thickness. Picture that we're making little discs. And we're going to be making discs going all the way down. They're going to get wider and fatter in the middle, and then they're going to go back down to narrow. Okay? Now, this little sliver of thickness we're going to call dy. Okay? The change in y, because this is the y-axis. If you go down the middle, this is y. Alright? That makes this distance going across from the center, this distance right here, we'll call x. So far, so good. Right? And we know that to get volume, you have to integrate the area. Okay? You're integrating the area. Now, how are we doing this area? Well, the area of this circle is pi r squared, which is pi x squared. So the integral of the circle, this area, of this circle is pi x squared dy for the measure of the thickness. So we have pi x squared dy. And for the volume, we are going to integrate this. Now, where are we integrating from? Well, this distance we'll call r, right? It's the r, it's the distance of the sphere. And it's the same distance down here. This is r. But on the coordinate plane, this point right here is 0r, and this point right here is 0 negative r. So you're really making these circles getting bigger, 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 going all the way down, smaller, smaller, smaller. This whole distance you're going is from r to negative r. So you're really going from r to negative r. All right, so that's our integral. That's what we have to work with. Well, this is with respect to y, and I have x. So I want to see how x and y are related to each other. So I go back. Now, if you look at this from the Cartesian plane, if this is x, and this is y, and this is r, right? Because it's still the radius of the sphere. How are these related? Well, by Pythagorean theorem, you're going to have x squared plus y squared equals r squared. So x squared plus y squared equals r squared. Right? So what do we want? We want it in terms of y. Right? And so what I want to do is get rid of this x. So I want to solve for x and then plug it in here. So I solve for x. So I have x squared equals r squared minus y squared. And I take this and I plug it in here. See this x squared? It's going to now be r squared minus y squared. Right? Isn't that what we have? R squared minus y squared. So here we are. So far, so good. Now we have to integrate this. Well, this pi is a constant, so I move it outside. So I'm moving the pi outside, and I have this. I'm going r to negative r, and what am I left with? I'm left with r squared minus y squared dy. R squared minus y squared dy. Now, we keep the pi. Put a big parenthesis. What's the integral of r squared with respect to y is just r squared y. And what's the integral of y squared with respect to y? It's y to the third over 3. And now we're taking this and we're going from r to negative r. Now let's figure that out. Okay? So, we were plugging in the r's for the y's. So you plug in the r into both of these and you get r squared r minus r cubed over 3. Alright? Take away, now we're going to do this part here, negative r put in for y. So you have r squared times negative r minus, now you put the negative r in here, negative r to the third all over 3. This is a kind of mess. So we have r cubed minus r cubed over 3. So here's what we have so far. We have pi times, we have r cubed minus r cubed over 3. That's this part. Minus, well, this is negative r cubed, so it becomes positive r cubed. So this becomes a positive r cubed. And then going back, we have this is a negative r cubed. This negative makes it a positive r cubed. And then this negative makes it a negative r cubed again. So it's a negative r cubed over 3. It's just a lot of algebra. Now what do we have? We have the pi right here. 1r cubed and 1r cubed is 2r cubed. And a negative r cubed over 3 and a negative r cubed over 3 is a negative 2r cubed over 3. Now what? Well, this is pi. And now we have to find a common denominator. Well, if I want to make this over 3, then I have to multiply this over 3. So this is 6r cubed over 3 minus 2r cubed over 3. Well, 6r cubed over 3 minus 2r cubed over 3 is 4r cubed over 3. So we have pi times 4r cubed over 3. And then for the final, just arrange it. 4 comes in front. 4 pi r cubed over 3. I'm exhausted trying to prove this. And you can do proofs in different ways on the same concept. Volume of a sphere. You could try this if you want. Instead of making the circles this way, try making the circles this way, where this thickness is dx, where this radius is going to be y. And then you could try it, do it this way, and see if you get 4/3 pi r cubed. Okay? Hey, this has been a tired Radical Dude, and I hope I was able to teach you something. Thank you.